Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome, everybody. It's my pleasure today to introduce Manjithan Kudla from the University of Michigan, who has done some very interesting work on stream computation. Is going to tell us about it today.
Okay,
thank you.
Thanks. Thanks, Sajim, for introducing me. I'm going to talk about my thesis work titled Streamroller, a unified compilation and synthesis system for streaming applications. As you all know, multicores are here and now. To quote Shekhar Borkar of Intel, he said cores are the new gates. He was referring to the fact that the number of cores on a chip are growing at the same rate as number of transistors or gates on a chip were growing a couple of decades ago. And the graph here shows, the timeline on the x-axis, and probably that was an exaggeration, but the rate still holds the same. Yeah, the x-axis shows the timeline, and y-axis shows the number of cores in the exponential scale. As you can see, say until year 2005, designers were happy with the single core, and they were able to increase the performance of single cores by throwing more transistors at that. But somewhere around 2005, the designers hit what I want to collectively call the complexity wall, so memory, ILP, and power walls. And they were not able to improve the performance of single cores any further. So to keep scaling the performance, they added more and more cores to the same chip. And as you can see, there has been a proliferation of multi-core chips in the past few years. Some of them are homogeneous, and some of them are heterogeneous with both like say accelerators and general purpose processors on the same chip. Let's see how these machines were programmed in the past. So all the Unicode processors were programmed using von Neumann languages, and I'm showing only C, C++, and Java here because they were the most popular. And this is not to say parallel programming was not done in those days. Parallel programming was there, and it was mostly targeted on supercomputers, and only scientists wrote like parallel programs. But when the multi-cores became commodity, all the companies out there are trying to, are scrambling to find out ways to program these systems. And I have shown a couple of examples here. And all of these systems, they follow different programming models. Some of them are language approaches, some of them are library-based approaches, and so on. But one buzzword you keep hearing, when you read about these systems, is stream programming. And let's look at what stream programming is. Stream programs organize the computation such that the computation is performed on streams. And a stream basically is a sequence of data records. For example, it could be the encoded macro blocks in an MPEG video. And the computation itself is called a kernel or a filter, and it's applied on streams. A kernel takes a stream as input and produces stream as output. And by far, most of the systems I showed in the previous slide, they were focusing on one kernel working on streams, whereas in my talk I'm going to focus more on where kernels can be chained together to form a big stream graph. And from a compiler point of view, basically a stream program is a coarse-grained data flow graph. And many work in the past have shown these stream programs are very amenable to aggressive compiler optimizations, and some examples I have shown there. And going back to the example streaming systems, I like to categorize them into two categories. One that target stream programs mostly for a single chip multicore, and that which target for a bigger system like a network of workstations or mainframes and so on. And my work, the Streamroller, it falls in the category on the left. I focus mostly on compiling stream programs onto single chip multicores. And I mean the examples on the right, IBM's SystemS project it's a mature research project which tried to organize the computation as streams, and their kind of applications are in the domains of financial markets and so on. And Google's Sawzall, Sawzall is the main language used by many application developers inside Google. And you generally don't seem to think of it as streaming, but basically Sawzall is a data parallel programming language, and it organizes the computation as as one piece of code working on many pieces of data. And the target basically is the network of workstations or the internet. But recently I was at CGO, and the Robert Greismer, who was one of the primary developers of Sawzall, he was saying, the developers or programmers are expecting features where you can chain the kernels in the Sawzall, basically feeding the output of one kernel to the input of other. And when you have such chained programs, you basically get a big stream graph, and that's very similar to what I'm looking at. And similar efforts are going on at Yahoo Pig and Microsoft. And the basic differences are the single chip multicores, they focus on applications which have high arithmetic density, very regular data, and examples include the graphics programs, media programs, and so on. And recently there has been a lot of buzz on GPUs, basically doing general purpose programming on GPUs, and examples include folding at home and computational fluid dynamics. Whereas the systems on the right focus more on applications which are more control intensive and unstructured data, like the internet data, and examples are search and continuous query processing for financial markets and so on. So in my thesis I address two problems associated with stream programming. One is compilation, the other is synthesis. So the compilation problem basically is you're given a stream program and a multicore processor. How do you find the efficient mapping of that program to the processor? And some of the challenges that you have to address there are, how do you find, or what is a good mapping of the computation to the cores, and where do you put the data, and the intermediate data, which memories do you map those data to? And in general, how do you orchestrate the computation and communication such that you observe some speedup? That's the bottom line. You've got to observe some speedup. And the other topic or the other challenge I address in my thesis is synthesis. When these streaming applications get implemented in the embedded domain, they usually go for custom solutions or hardware solutions. And it makes sense for embedded domain because they want high performance but at relatively low power budget, so they usually go for hardware solutions. And it turned out that some of the problems are very similar. You still need to find out a mapping of the computation to the hardware blocks, and need to find out the mapping of the intermediate data, where to put the intermediate data in. And and in addition, you might have to find out what each block of the hardware looks like. But it turned out that all the problems are very similar. By adding some kind of a cost sensitivity to all the scheduling and the mapping problems, you can easily change the problem of compilation into synthesis. So these are the two topics I address in my thesis. And to this end, I have developed this Streamroller software infrastructure, which has multiple front ends and multiple back ends. One of the front end is C, stylized C, where basically the programmer writes sequential C, but with some assumptions on what constitutes a filter, how will you transfer data between one filter and so on. And the other one is SPES, which was developed by my colleague who was working on this infrastructure for software-defined radio. So basically, it's C++ with, again, sequential C++ with some assumptions on what constitutes a stream and so on. And the one other language I'm as a front end is the Streamit language, which is basically an explicitly parallel programming language, which has a streaming as a primary or a first-class construct in the language itself. And the backends, the custom application engine is for the synthesis. Basically, you take one of these stream programs described in the languages and produce a custom hardware for it. And the other target that I specifically target is the SODA, which is basically the low-power multi-core architecture for software-defined radio application. And the regular multi-cores like cell processor, the core-to-door and so on, which are regular commodity multi-core processors. We have backends for those two. Different parts of this work has been published in different places, but today I'm going to focus on this part where I take a Streamit program and map it down to a multi-core, especially the cell processor. So any questions until now? So I've been talking about stream programming in the abstract, but I'll like to make it more concrete in the slide. Basically, the programming model I'm focusing on is the synchronous data flow, and the language is Streamit. In Streamit, basically you describe the computation in terms of a data flow graph, coarse grained data flow graph, and when you zoom in into one of those nodes, basically it's called a filter in Streamit. It's an atomic piece of computation. It has its own address space, it has its own flow of thread of control, and you describe that atomic unit of work in terms of a class. And here I have described a FIR filter, which basically does the finite impulse response on streaming data, and all the computation to the outside world is made explicit using FIFOS in this case. And you basically push and pop from the FIFOS when you want to transfer data between a different filter and yourself. And the main difference between there have been different streaming models, and the main difference or the distinct feature of this SDF is that every invocation of this filter, you push and pop constant number of items, which makes it amenable to static schedules. So you can basically given this big program, because every time as a filter is invoked, how many items it's going to push and pop, you can come up with a static schedule.
So those can't be, runtime constants? You can't put n there?
They have to be static. They can be, no, they have to be compile time constants. You can put n there, but when you form the graph, the n has to be known.
No, okay, so you would do like runtime specialization in that case?
No, at compile time, n is known. Okay. So, when you want to, so it's basically.
You don't deal with symbolic. It has to be really a constant.
No, it can be symbolic, but when you define this class, it can be symbolic. But maybe when you use this class at a particular place, instantiate it, you have to know n.
Okay.
Yeah. So basically, symbolic things gives you like productivity, but you can use the same code multiple places.
Okay.
So. And if you see, the only variable this piece of computation modifies is the sum variable, which is a local variable, and there is no other carried state across invocations. And such filters are called stateless. And I'm going to leverage this fact that it's stateless because if a filter is stateless, what you can do is basically run multiple copies of this filter in parallel and concurrently. So instead of conceptually, you can think of this filter pulling one data item, doing some computation and pushing one data item. You can basically pull, say, 4 items, do the computation of for those 4 items in parallel, and then push 4 items. As opposed to the other case where if this weights input was not input but a local class member, and that was changed every invocation, then it becomes what is called stateful. And from a compiler point of view, basically what it means is there is a dependence loop on that node. So basically every invocation depends on the previous invocation, so you basically cannot execute the copies of that in parallel. Okay, so yeah, from a structure it's very it's obvious where the parallelism is, but I'll make it clear. So when you have a structure like that, when one node is feeding 2 nodes, I'd like to classify it as what is called task parallelism. And when you have this stateless filters, basically you can execute copies of them in parallel, and like to categorize that parallelism as data parallelism. And possibly the most important one, which arguably encompasses both these task and data parallelism, is the pipeline parallelism. And this comes about from the fact that this entire computation is going on, is run for every item in the input stream. So basically what you can do is you can run the computation on these different items in parallel.
I'm sorry, I don't understand the difference between data parallelism and task parallelism.
So the user or the programmer, when he has put a structure like that, where there is a kind of fork of data, and then these two basically can be 2 different computation. They can be anything.
Green and red.
Yeah.
Right.
Whereas data parallelism, it's the same computation, but it's run on.
Oh, I see. So it's SIMD versus whatever. Yeah, I see.
Yeah.
Versus.
So this kind of a thing is not made explicit in the program. You can derive that if you want. If you see a filter which is stateless, you can basically do execute multiple copies of that in parallel. Yeah.
So in practice, what fraction of the filters that people use are stateless?
Okay, that's a good question. In the benchmark suite I looked at, it turned out that about 50% of the programs, the entire program, all the filters were stateless. So that was an easy case. Whereas in real programs, you have this idiom of shifting or sliding window. So when you have sliding windows, a lot of signal processing applications have that idiom, so all of them become stateful. And in programs like MPEG, for example, you got to remember what you did for the previous frame and so on, so they become stateful also. So I would say a lot of applications are completely stateless, and in some applications there are stateless filters, but there are also stateful filters. So. And I was talking about this pipeline parallelism. I mean, if you think about it, it's not very different from the do across parallelism that you might have come across, in high performance Fortran. And if all the filters happen to be stateless, then it's a do all. You can basically execute this computation in parallel across all the data items. So good. So we have all this parallelism, but when you want to compile it down to a multicore, you would see a speed up only if you are able to divide your work into equal parts. Parts which you can run concurrently. So that's one of the challenges that that you have to address when you want to compile these stream programs to multicores. And the other challenge is, when you try to divide your work into equal parts, you are invariably going to put a producer in a processor and a consumer in a different processor, and you got to worry about waiting for the producer to finish, synchronize, and then transfer the data over, and so on. So this communication, synchronization, and storage management, those are the challenges that you have to address when you want to compile these things to multicores. So to address these challenges, I developed this method called the stream graph modulo scheduling, which takes a stream program and compiles it down to multicore. And my target specifically is the cell processor. That was interesting because this project was being done as a part of the software-defined radio project, and the architecture they had called SODA was very similar to the cell processor's architecture. So basically, the main distinguishing feature is the disjoint address spaces. So each core that you want to run your computation has an address space which is disjoint from the rest of them. And you can basically copy, or you have to have explicit copies, DMA copies, to transfer data over to yourself or to other processor. And if you're wondering why the name modulo scheduling is a very popular software pipelining technique used in compiler backends. So where they use this technique for scheduling instructions to function units. And I mean, it's kind of that's kind of an analogy here. I mean, I treat the instructions in the same way as I treat the filters in the same way as instructions, and then I treat the coarse the same way as the function unit in a VLAW processor. So that's the reason I chose the name modulo scheduling for this. And the SGMS itself is divided into phases, and I'm going to go through each of these phases in the next few slides. But I want to state some assumptions up front. I get this questions all the time. So does it work for these kind of applications or different kind of architectures? But most of the SGMS decisions were made because we had a particular set of applications in mind where the work functions are kind of static, which means they don't the runtime don't change across data. So basically, data independent work functions. And also assume a high bandwidth interconnect, which the cell processor happen to have, which means you can have a load over a DMA, and the observed latency for transferring data is quite low. So which means if you have interconnect where the latency is going to be high, then this may not be directly applicable. And the other one is the assumption is that the cores can run independent threads efficiently. So this doesn't apply directly to GPUs because GPUs want the control flow in each of these threads to be the same. So having stated those assumptions, basically this is like a one-slide overview of what the system or what the algorithm is. Basically, you're given a stream program, you're given a bunch of cores to run on. The first step is to divide up your work into equal parts, almost equal parts, and then run those equal parts concurrently with each other in the cores. And invariably, okay, so once you do that, if you are able to run those if you are able to run those parts concurrently, then what you're going to see is you can run them faster. So you're going to see a runtime of T4 compared to a sequential execution, which is T1, and your aim is to get T1 over T4 approximately equal to 4. And to do that, you're obviously going to incur some data transfer overheads, because you're going to put producers and consumers in different places. And also you might have to do some to make sure that producers execute before consumers. You might have to fill the pipeline using some prolog, and drain the pipeline using some epilogue. And I'll go through this in the next few slides. So the first one is the processor assignment. Here the main aim is to do load balance. So basically you're given a graph, and you want to divide it up into equal parts, and this seems awfully familiar. Why can't you do a graph partitioning or something like a bin packing? And I'll show you why these techniques are not directly applicable here. I'm showing you a simple stream program. This is what the programmer conceived of. When he wrote the program, this is what he had in mind. He had this logical division of work in his mind, and it happened to it happened that the amount of work done in each filter is shown on the numbers on the left. For example, B did 40 units of work and C did 10 units of work, for example. And I represented more graphically. So B had this lot of work, and this is not surprising, because when the programmer wrote, he had some logical notion of how he wants to divide up the computation, but doesn't know how long it's going to take to run on a core, for example. And if you have two cores, any of these methods like graph partitioning or bin packing is going to give you that partition. Basically, it's going to put B in its processor by itself, and then the rest of the nodes on the other processor. And the maximum speedup you can hope to achieve here is, even if you're able to run all of these two chunks of work in parallel, you can get a speedup of 60 over 40. 60 is the sum of the work in all the cores. You probably can get a speedup of 1.5. But however, if you can modify your stream program such that the B happen to be a stateless filter, maybe you can divide its work into two parts, B1 and B2. You will incur some extra overhead, in scattering and gathering. Here it's called split and join, but you can still maybe you can use the same methods to get a different partition where B1 and B2 now are in different cores. And here the speedup you can get is 60 over 32. The 2 comes from the fact that there is a small overhead of scatter and gather. So you can hope to achieve a speedup of approximately 2 here. So if you think that is a made up example, I'm going to show you in real programs, and I'll go back to the what the applications are in a later slide. But in real programs, if you try to take the original program, how the programmer conceived of it, and try to divide up into equal parts, say 2 parts, 4 parts, and so on, the speedup you can get for 2 and 4 is okay. You can get a speedup of 4, but when you go to 8 and 16, it's not amenable to getting divided into equal parts. And the reason is, for example, in one of those benchmarks, 15% of the work was done in one filter, and the maximum speedup you can get is 100 over 15, which is 6.7. So you cannot scale by just taking the programmer conceived graph and trying to divide it into equal parts. So what choices do we have? So let's say you have a program, and you find some data parallel or a stateless filter. Let's say using some heuristic, you try to divide into 3. You decide that you can divide into 3 parts, and maybe pick a different filter and then divide into 4 parts, for example. But to know whether you're done, or whether this is a good transformation of the program, you have to actually do a assignment. You basically have to try to divide it into equal parts, and then answer the question whether did you get a speedup of 4. And if you didn't, maybe you have to go back and do some more heuristics. And this is a classic case of a circular cause and consequence, basically a chicken and egg problem. And our solution to that is an exact solution, basically exact solution based on integer linear programming. It combines these 2 phases, trying to decide which data parallel actors to divide into, to replicate, and the problem of actually assigning those filters to the cores into the same problem. Basically, for every data parallel actor, it basically considers different versions of the actor. So maybe that actor divided into 2 or 3 or 4 and so on. And the overheads of the scatters and gathers, or splits and joins, as I call them here, they are also factored into the exact solution. So what you do is you given the program, you form some equations, and out comes two answers. One is the number of times you have to split each stateless filter, and where those filters have to go. So which P you have to map those filters. And the objective here is to minimize the maximal load on any processor. So that determines your throughput. So looking at a processor assignment, if you look at the processor which was maximally loaded, that determines your that's the bottleneck basically, and that determines your throughput. So that is minimized. And once you do this, you get this nice equal division of work between all these processing elements. So the next phase I'm going to talk about is the.
So I don't use further scheduling problems, and you made an analogy between, cores and functional units. Is your algorithm, can you reduce your algorithm to a previously known algorithm? I mean, what am I missing here? From a high level, it looks like, with your analogy, maybe what you're just doing is just taking some existing algorithms and lifting them up. But I have a feeling that's maybe not the case.
Yeah, you're right. The analogy holds true just by thinking about these filters as instructions and the function units as the cores. But they have totally different characteristics. An instruction is, instructions execute in lockstep, and they have a fixed latency. Whereas these guys, the filters, the latency in number of cycles is quite long. So you cannot think about, so in modular scheduling, they do what is called the cycle by cycle or instruction by instruction schedule. Yeah. So they take one instruction, they fill a few slots. Yeah. Whereas here, because the number of cycles is so many, you cannot think about doing a cycle by cycle schedule because the total cycle length is too much. And the other fact is, you don't think about replicating these instructions, meaning you don't, So
can you go to the previous one? So how do you get all these A sub I, J numbers?
Oh, I deliberately didn't put all the details here because it's going to be boring. All the details are there in my paper, PLDA paper. But, just as so for every filter, I consider multiple versions of that. So one of the suffixes chooses the filter, one of the suffixes chooses which version that you want, and other one of the suffixes chooses which of these copies in the version, and so on. So
suppose the user is given the cost for the entire filter, right? You somehow have to figure out, when you split it into 5 pieces, what the overhead should be and what each of the pieces cost is going to be, right?
So each piece's cost is a constant because when you divide into 2, it's half each. So.
But again, when you somehow have to have a model of how much data you're sharing, what the cost of getting the data transfer. Yeah, you have to explicitly model all those.
Yeah, the cost here is the amount of time it takes to execute that filter. So when you divide into 2 parts, now the cost is divided into 2. And there is the small overhead for the scatter and gather. That's a constant because we know exactly how many data or how many elements are transferring to different places. So, yeah, like I said, this works if the costs are all static. If each of these filters is doing data dependent work, then this may not hold true.
So you're not taking into account the possible variation execution time of each instance of a filter.
No.
Right.
That's
so
one of my
you
assumptions.
Observe, some variability in the execution time, and how much?
Fortunately, we didn't, because the kind of applications that I benchmarked this system or this method against were all FFT and MPEG and so on, which had that property that the execution time of each filter is constant across.
So even with the memory system involved, you think you'd have cache misses and things for each instance, right?
So that's also part of my assumption. So I'm running this on the cell processor, and cell processor doesn't have any cache. So
you have complete control of the memory system.
Yeah.
If you did have a cache, would that change your results or change your strategy?
So the variability of the runtimes, that didn't have much of an effect. So I tried running this on a regular core 2 quad and so on. The thing that had effect was, once you run a producer on a core and a consumer on a different core, there are all these cold misses because, the producer has produced a lot of data and the consumer is now going to that's one of the main reasons for variability. But the data that each filter is accessing, the local data, that didn't have much of a cache effect. So you're right. Different targets, the variability might be important, but the one that I targeted didn't have that problem. Okay. So yeah, we have this nice division of work across different cores. But to achieve any speed up, basically you have to execute this chunks of work in parallel or concurrently, and also all the communication should be overlapped. And I'll show you that just assignment of these filters to processor is not sufficient information. Okay, let's say you have this simple stream program, and B happens to do twice the work of A or C. So you would have this nice division of with these filters between two processors, and you will see a speed up only if you are able to execute these two chunks of A and C and B concurrently. And if you want to ask the question whether you can execute A and B concurrently, the answer is no, because A is producing some data and B is consuming some data. Okay, so how about because we know this entire stream program is getting executed on different data items, how about executing iteration 1 of A, wait, and then run iteration 2 of A, and then execute the iteration 1 of B concurrently with A2? And the answer is no again, because you have this intermediate transfer. Basically I'm looking at this distributed memory machine, so you have to transfer over the data produced by the first iteration and then run B. So you still cannot overlap A2 and B1. But no, it's easy. You can just extend this notion one iteration further. Basically, you can overlap the third iteration of A and the first iteration of B, while the transfers of the previous iterations is still going on. And so this is the information that is missing from the processor assignment. So basically, you can overlap only iteration I plus 2 of A with iteration I of B, and this is what is being done in this the second phase, the stage assignment phase. So it turned out to be quite simple. Basically, you basically divide your entire computation into what are called stages, and stage the rules for choosing the stages basically are if you have a producer and consumer in the same processor, you basically make sure the stage for the consumer is larger than the stage for the producer, and this basically preserves causality or the producer-consumer dependence. And if you have this case where have a producer and a processor and a consumer in a different processor, you leave one stage for the DMA to occur. So basically you put the DMA in a stage greater than the stage for the producer, and you put the consumer in a stage greater than the DMA stage. So this ensures that you can overlap the computation with communication. And a simple data flow traversal of the stream graph can give you just start with 0 for the first node. When you go down, you can start assigning increasing. I'll show an example in the next slide. So let's say you have this simple example that we saw before. All the red nodes go to processor 0, and all the blue nodes go to processor 1. You basically choose stage 0 for all the red nodes, but because all the consumers now are in a different processor, you put all the transfers in stage 1 and the consumers in stage 2. And similarly, because the D node is in a different processor, you put the DMAs in stage 3 and the consumer in stage 4. Excuse me.
Is there any sort of bad consequences from doing all the DMAs at the same time?
So this example happened to have that effect that all DMAs fell on the same stage. Yes, there is, because there is limited bandwidth for doing all the transfers. But for the stealth processor, I found that you can have, so in the steady state you can have about 12 transfers going on at the same time, and you didn't still saturate the ring or whatever. So the other way of looking at it is if you knew that the DMAs have limited bandwidth or you're going to take long latency, then you might have to treat these as units of computation, and you're going to treat them as a first class construct and then try to schedule them also. I didn't have the problem because DMAs are fast in the cell processor. Oh, sorry.
So in that picture, C and B2 cannot overlap, right? They're executing on the same processor. Is that what the color code means?
Oh yeah, they don't overlap. I mean, but whatever gets assigned to the single processor, they all execute in sequence. But across processors, they are overlapped.
And so the optimal solution you had without pipelining, does it carry over to the case even if you have pipeline? Or in the sense, maybe if you add these constraints, then you can get an optimal solution, a different optimal solution.
So the optimal solution said that you execute A, S, B1 and D in one processor and C, B2 and J in another processor, but you execute them concurrently. Because of this stage assignment, what happens is this basically allows you to execute them concurrently, not the same iteration but different iterations. So what would happen is you'd be executing iteration 1 of A, S and B1 in processor 1 while you're say iteration 3 actually, while you are executing iteration 1 of these nodes on processor 2. So basically these things get executed in parallel but not the same iteration. And the stage assignment is the one that gives you the information on what iterations to overlap. And the next is the code generation, which ties all these things together. Basically I target the SPEs, as they are called, of the cell processor. You have up to 16 SPEs on this QS20 blade server, and the main challenge here was to making this collection of these independent threads implement this software pipeline that we came up with in the previous 2 stages. And I basically adapted the kernel only code schema. I mean, this Modulo schedule has this nice simple way of representing these things, and I'll show you an example. Okay, so this is basically the code that runs on each of the cores, and I will deconstruct it for you. Basically there's this outer loop or the driver loop which goes through all the input items in the input stream, and there's this thing called the staging predicate, or this array which controls what stages are active at each core, and basically it's a bit mask. So initially stage 0 is active, and every next iteration you do this left shifting of this bit mask, which is implemented as an array, and more stages get activated. So these if conditions control what gets executed. They are basically predicated by this stage array, and every active stage you do some DMA, and you do some the work for the filter. And finally, after you are done with the stage or one iteration of the function, you basically wait for all the DMAs to complete. And so this makes sure that you do the waiting only once. And finally, to synchronize across all the processors, you have this barrier. I'll show an example basically, which shows how these things work. So the same example I showed before. The main thing to note here is this steady state. What happens in the steady state is whatever the processor assignment told should execute in parallel are actually executing in parallel, and all the data transfers are also running concurrently. But if you see some iterations before, not all of them are active. Because of this stage assignment, you make sure that all the producer-consumer dependencies are satisfied. But also, in steady state, you're able to execute all these things in parallel. So, yeah. Sorry.
How much would it have saved you to unwind the loop and so get the conditionals out of the inner loop?
Sorry.
How much would it have saved you to unwind the loop and get the conditionals out of the loop for the initialization of the pipeline?
I didn't do that experiment, but I would guess very less, because the if conditions. I mean these guys. I mean the times taken to execute these guys are quite long compared to if condition, branch mispredict or whatever you get by doing the conditions. But that's a good question. I mean I didn't do that experiment. I mean just because these guys took a long time to execute their code scoring. I would say basically they are for loops with trip counts of about thousands of, and in each of the for loop body they do they call math functions like sine and cos. So they're, yeah. And these are the benchmarks. Basically, I took the Streamit benchmark suite. The example programs are like the streaming implementations of these kernels like DCT, FFT, and so on, and bigger signal processing applications which use those DCT, FFT. And one of the bigger programs is the MPEG-2 decoder. It basically is a decoder for the iframe of the standard, and other applications like encryption, and there is this parallel bitonics out there. And the main feature is these the filters ranged from about 30 to 90 filters. So that's how big the stream programs were. And my target was the QS20 blade server, which has two cell chips. So I have like 16 SPEs to target. I basically used the Streamit front end that the MIT guys had developed, and I wrote the backend for the cell processor. Basically, it produces C files which you can compile with GCC and run them on the cell processor. And these are the kind of results I get. So the x-axis is the benchmarks, and the y-axis is the speed up. And I show the results for 2 SPEs, 4 SPEs, and up to 16 SPEs. And it's not really surprising that you're almost getting a near linear speed up. And the reason is because the processor assignment is able to do a good job of taking the program, transforming it by looking at all the stateless actors and dividing them into multiple parts, and then actually doing a division of the work across processors. And the stage assignment obviously is going to give you make sure that all these chunks of work can execute in parallel. And some of the benchmarks didn't get 16x speed up, and the main reason was these the split joints. These basically, when you look at a stateless filter and when you want to divide it into multiple pieces, you have this extra overhead of scatters and gathers, which was not present in the original program. So that overhead took that was a small overhead that we had to pay for actually dividing it into equal parts. And the other was the barrier. There is one barrier across all the SPEs, and in the cell processor it happened that the barrier was not that high. So I could do one barrier, about 2 million barriers in 1 second. So that overhead was not that much. So we were not able to. That was not a big problem on the cell processor. And the question I get asked all the time is, how do you compare your ILP with a greedy method? The first question also is, how long does it take for your ILP solver to actually do this work? And it wasn't that high. For 16 processor case, it was about less than 30 seconds for all the benchmarks. And I tried to run this experiment on trying to divide this work into 128 parts, and it was 16 minutes. 16 minutes is arguably high, but I didn't try to do any fancy optimizations on the ILP itself. So, and that's something I'm looking at now. And compared with the greedy, the greedy solution basically is the previous state of the art. They tried to take the stream program, try to greedily do a graph partitioning across all the cores, and as you can see, the greedy was able to was quite close to the exact solution in a lot of cases, whereas in some other cases it was up to 35% worse. And I found that the greedy performs pretty close to exact on lean graphs, meaning which was like a sequence of filters connected to each other. And for fat graphs where there's a lot of parallelism and a lot of splits and joins, the ILP was better up to by 35%. Okay, so since then I've been working on trying to extend this to different in different directions, and one of the extensions is trying to scale this SGMS to more cores. When you have more cores, the problems you're going to run into are less bandwidth for between cores and maybe less bandwidth to global memory. And the other one is this was interesting to us because the SDR project, the solution we had much less memory compared to the cell processor. So when you have this kind of a system, targeting the same SGMS was also a problem. And the other is I also focused on trying to extend this to other platforms like FPGAs, GPUs, and so on. And as you can see, I mean, both these problems have the same kind of requirements. I mean, if you have more cores, you're going to have less bandwidth, and if you have a constrained memory system, you're going to have less memory. So the main, it happened that the solution needed for both of these directions is the same. Basically, reduce the memory requirements of the SGMS schedule. And for more cores, you have to scale the LP formulation, and the 16 minutes of 128 cores is probably not that good. So I'm also working on that. So let's look at this part. So the reducing memory requirements of SGMS. So how much memory does it require? Where is the memory needed for this schedule? So when you have a schedule like this, basically when you have 3 nodes, your steady state is going to look like that. But what you're going to do is you're going to execute 2 iterations of A even before the first iteration of B is executed, which means there are 2 blocks of data that is live, that is produced, not yet consumed, corresponding to that edge. And in the general case where you have a producer in stage I and a consumer in stage I plus k, you're going to have k blocks of data which has been produced but not yet consumed, and you need to store them somewhere. And it's easy to see that the more instances of such cases you have, where you have a producer and a different processor and a consumer and different processor, you need more memory. And the main focus was to try to reduce the number of edge cuts that you had when you tried to divide your work into equal parts. So the problem of minimizing the memory requirements basically translated to minimizing the number of edge cuts that you have in your schedule. And there are these 2 requirements which are opposing. Basically, when you want to have a good load balance, you need more freedom in assigning your filters to different processors, but when you have minimal edge cuts, you restrict the load balance because you have to put more things together more and more. And the current approach that I have is basically treat the load balance as a first class criterion. Basically try to achieve as much as load balance as possible, but then retroactively go back and see if you can try to reduce some edge cuts but still maintain the same load balance. And this is eye candy. I mean, basically there are 2 work divisions. The red nodes go to the red processor and blue nodes go to a different processor. The fact is both of them have the same load balance. So both of them put 50% of the work in the blue processor and 50% of the work in the red processor. Whereas the number of edge cuts there was 29. By doing some retroactively changing the assignment but still maintaining the load balance, you can get the number of edge cuts to be 7, and it saved about 70% of the memory. So this schedule requires 75% less memory than that schedule, whereas both of them actually have the same speedup.
So what was the algorithm for minimizing the edge cuts?
So I'm given an assignment. I'm given already a partition.
So you have the thing on the left.
On the left. So what I do was formulate it as an ILP again. Basically, try to move each. Try to find a different place for each of the nodes, but the constraint is you still need to have the same load balance. So whether you can move things around and see if you can get a less number of edge cuts, but still maintain the load balance that you got originally. So
your requirement was it had to have exactly the same balance?
Yeah.
So what would happen if you had some kind of trade-off that you could have, you could give up? Did you look at that?
Yes, I mean the trade-off here was 0, meaning there was no good. Okay, the trade-off basically is if you can not have some load balance, right? That's the trade-off. So whether you can get lesser number of edge cuts if you were willing to forego some load balance. What happened was, because on the cell processor, because of the fast interconnect, the transfers were not that big of an overhead, which means if you had any imbalance in the work to begin with, you're going to see some slowdowns, or your speedups are not going to be that high to begin with. Whereas,
You're saying that the speed up is disproportionate to the imbalance in some sense. In other words, a little bit of imbalance gives you a lot of.
No, it's not disproportionate. It is proportionate. But any gains that you could get by allowing some load imbalance and getting less edge cuts, that's disproportionate. Meaning you won't see. You're better off making some perfect load balance and getting more edge cuts than allowing some imbalance to begin with and getting edge cuts. So, I mean, that's again specific to the cell processor because of the fast interconnect. If you had to do this for a case where the bus bandwidth was not that high, then you might have to do some integrated method where you were treating both of these things as a first class criterion. Okay, so other targets. So I have been working on I mean, this has been exciting because it's almost going to go into a product. The Artbag is basically the productization of Michigan. I mean, my professor and Trevor Mudge were working on a solution for the software-defined radio, and ARM is going to make that into a product called Artbag, and they want a solution. So basically, I'm trying to integrate my thing into this ARM's compiler toolchain that they have for that Artbag processor, and the from a high level, the architecture looks exactly the same. You have a bunch of cores having their own local memories, but there are some differences on how the DMA engine is done and so on. But exactly, I mean, the same solution was able to apply there. But some of the other things that I had to worry about when I tried to integrate into the toolchain was, these the soft radio things have these different modes of operation: idle, standby, and active. And in each mode, the computation done is different. So basically, you have these 3 different stream graphs to schedule, and one of them is only active at the same time. So you got to worry about some extra software issues. And the other thing is these things have real-time requirements. You probably don't need perfect speed up, but you have to have this real-time. You basically have to execute one iteration of it in whatever number of seconds. So that was some of the things that I also worked on for this project. The other target is FPGA. I mean, this is exciting because all these new systems, they're thinking about putting this programmable fabric on the same chip as the processor. So my contribution here was trying to minimize. Here our approach was to just basically take one filter and map it down to one block of hardware in the FPGA. And my contribution here was trying to minimize how many FIFO, basically because FIFO is a costly resource on FPGA. Trying to minimize that was one of my contributions. And the other one is GPUs. So if you looked at my code schema before, basically each of them execute independent threads, and that's not very good for the GPUs because they need these similar looking code running on all the cores. So I slightly changed the code schema, and the code schema now looks like all the threads do exactly the same number of work, and they have identical control flows. But they need to do more synchronization because for every stateful filter, you need to transfer data, basically the state from a different place. So basically I've been working on this. I don't have any results for this, but the initial results seem interesting. To summarize, I developed this the stream graph modulo scheduling method for multicores, compiling stream programs to multicores, and I have this phased approach where you take the program, do some transformations, and then do the mapping, and also make sure that the communication is all hidden. And on 16 cores, I was able to get a 14.x speed up, and I've been working on these extensions to scale to more cores and constrained memory systems and so on. And I also worked on other targets, the SOTA, FPGA, and GPUs.
So the programs that formed your benchmark suite, so they were written in which language again?
Streaming.
And so you didn't make any source code modifications to those, you just implemented the optimization. So these were just standard benchmarks, you didn't have to modify them in any way for your approach?
I mean, that was one of the I didn't write them myself, they were all written before, but this is the complete end-to-end system. You can take any stream program and run it directly on the hardware. So
So when you talk about scaling to more cores, so what are the issues there that you have to address?
Yeah, so like I said, the first step, one of my steps is this ILP formulation, which probably, arguably, so it's about 15 minutes for 128 cores now, so that the compile time is an issue. And the other issue is, when you have more cores on the same chip, you're probably not going to have the same kind of bandwidth across the cores, and maybe the bandwidth of the global memory is not going to be that high. So I had to do this trying to minimize the amount of memory required for this schedule. So I did some edge cut minimization and so on for minimizing the amount of memory.
So have you thought about programs? So there's these streaming programs in this suite, but some of this is going to depend. You're getting great speed up, obviously. Some of this is going to depend a lot on how much sharing goes on in terms of the stream programs.
Sharing between what?
Well, so between the different, I guess the question is sort of one of the ones that Jim asked earlier. Sort of, if you look at these filters and how many of them can be parallelized, etc. So have you sort of tried to understand what the limits are in terms of the amount of state and things like that you can compile with your technique and how it breaks down?
So when the programmer writes its original program, right? So there is this logical division of work. So logically, you need to do this FIR followed by FFT or something, and then followed by that. When you have such a division, then it's easy to express such division in the stream program, but it doesn't directly map down to performance. You need to do these transformations, find out data parallel or stateless filters, try to divide them into equal parts to all saturate your the processing resources you need, and so on. So just like any other effort in doing parallel stuff, if you have this one filter which is stateful and it's doing say 50% of the work, you cannot get a speed up of more than 2 for that, because you need this. You have this one bottleneck. So my work mostly has been on when you have equal work, or when you don't have bottlenecks like that, you still need this intelligent way of dividing your work and making sure that it runs, all of them run parallel. So yeah, my work mostly has been on the compilation part and not so much on actually. So for example, if you have reductions or something which is not data parallel, you can probably do some high level transformations to make that parallel, but I don't do such things. I'd like to talk about some future work. Hopefully it's in line with what Microsoft is trying to look at. So basically, until now, I've been focused on this one model, and then the static compiler for that to multicores. Whereas in reality, there is this different levels of software abstractions. You have this starting from the domain-specific models all the way to parallel libraries and so on. And my focus mostly has been on the static compiler part. But whereas for this other kind of streaming systems I talked about before, the dynamic streaming system, the current approaches has been mostly on handle everything at runtime. Basically, you're given this program, the runtime handles everything of doling out the work to different cores and so on. Whereas I think there is a nice role for the static compiler to play there. So this integration of these three things, the static compiler can probably restrict, because it has a global view of the application, it can restrict the choices to the runtime systems. Maybe it can place the producer and consumer close by, or maybe for a system where each core or each chip is a multi-core and you have this network of workstations of these things, maybe it can come up with a static schedule for the single chip, and across different machines, maybe the runtime system can handle that well. And even on a static compiler, I would say we should go back and revisit some of the auto parallelization work that has been going on for the past 20 years. And the reason basically is you have these new architectures, which mean you have new challenges and probably have more new opportunities. And I have I've had some experience in this polyhedral model, which basically it's basically can represent more types of loops, and it can do transformations in unified fashion, and using that model to come up with a good schedule for multicores is an interesting idea. And obviously I'd like to extend my my view to these different layers. And one work that I have been recently involved with is deadlock prevention for programs based on threads. And there seems to be this nice application of this Petri nets and other control system principles to deadlock prevention. And I've been working on some with my colleague to do some deadlock prevention and race detection for threaded code based on Petri nets and linear programming. And with that, I'd like to
Any other questions?
So, how close are the dynamic techniques to the static techniques? So, ballpark, we saw your speed up is really quite close to the actual parallelism. Well, where are the dynamic techniques?
So, for applications where the filters are all data independent and take the same time, any dynamic technique is going to have some overheads. So you probably won't see the same speed up, which is based on a runtime technique.
So could you give me a ballpark idea of how
So I know of some effort at MIT to do this all dynamically, and from talking to them, I hear the overheads imposed by the runtime system is about 10 to 30%. Basically, because it may be because of their artifact. They have this work queue where every every core looks at, pulls off work from that, and then starts running the core. So that overhead is about 10 to 30% for different applications. I mean, if you think about the other extreme where
30% overhead from doing the optimization at runtime,
yeah.
And what is the speed up that you get? Like the optimization is probably less perfect, right? Because it has to be done quickly and with not less information.
Oh, yeah. Yeah, I don't know about that. I mean, I just know the overhead imposed by this. So even if you had a good, even if the dynamic system did the same kind of work division as what I did, you're going to see a 30% reduction in speed up. So yeah, you're right. I mean, maybe because it doesn't have a global view, it probably won't get the same work division across cores and so on. So you're going to see some slowdown because of that. Yeah.
Other questions?